Hello and welcome to The Explainer. Today we are diving deep to answer a question that pretty much defines our entire modern world. How in the world did we learn to talk to machines? We're going to trace the really surprising history of programming, starting with threads of fabric and ending with the code that weaves our digital lives. So let's kick it off with the most fundamental question of all. At its heart, this is really it. This is the whole problem. Before a single line of code can be written, you have to solve a communication puzzle. It's not about syntax or semicolons, not really. It's about giving a machine a perfectly clear set of instructions that it can follow without any confusion. And the first people to truly crack this, well, they weren't computer scientists. So let's start with section 1, the first automated machines. Our story begins in a place you might not expect. We're literally weaving the future. The genius of this idea was its simplicity. Jacquard created these cards with patterns of holes punched into them. A hole meant a hook would lift a thread. No hole, the thread stayed down. It was basically a physical if-then statement. For the very first time, a complex process could be stored, automated, and run by a machine. This was absolutely revolutionary. And this is where the idea makes its first huge leap. Decades later, a mathematician named Charles Babbage saw Jacquard's Loom and had this incredible flash of insight. He thought, wait a second, if punched cards can weave fabric, they could also weave numbers. He took that exact same concept and adapted it for his theoretical machine, the Analytical Engine. Now, even though it was never actually built, Babbage's design from 1837 was just mind-blowing. It had a mill, that's basically a processor. It had a store, that's the memory, a control unit to read the instructions, and input/output. I mean, those are the fundamental parts of every single computer we use today. He had designed a general-purpose computer more than a century before the first electronic one was even a thing. Okay, section 2, the birth of the algorithm. So Babbage had designed the hardware, but a machine, it needs a mind. And this is what led to the birth of the algorithm and to the very first programmer. So while Babbage saw a super-powered calculator, Ada Lovelace saw this. She realized the machine could work with any kind of symbol, not just numbers, but music, language, you name it. For her, this wasn't just about crunching numbers, it was about the idea of general-purpose computing. And this is the key point. Lovelace was the very first person to see what software could truly become. And to make that vision a reality, Lovelace had to formalize the whole process of giving instructions. And she did that using the core concept of the algorithm. You can just think of it like a recipe, a very precise, ordered, and limited set of steps to get a specific result. Every single app on your phone, every website you visit, it's all built on this fundamental idea. So, why do we call her the first programmer? Because she actually did the work. She didn't just dream about it. While she was translating an article about the Analytical Engine, she added her own massive set of notes. And right there, inside those notes, she wrote out a detailed algorithm to calculate something called Bernoulli numbers. It was the first published algorithm ever made for a machine. She even dreamed up concepts like loops, repeating instructions, and conditional branches, the if-this, then-that decisions, that are basically the DNA of all modern software. Let's move to section 3, the language of machines. So for about the next 100 years, programming was a physical act, plugging in wires, flipping switches. To take the next big leap, we had to move from wires to words. And this led to a really important split. The first languages, like assembly, were low level. They were super close to the machine's own ones and zeros. Very fast, but incredibly difficult for a person to read or write. The real game changer was the invention of high-level languages. These used words and formulas that were much closer to human language, which made programming way more accessible. But there was a catch. You needed a special program, a translator, to turn your human-friendly code into the machine code the hardware could actually run. And the pioneer here was FORTRAN. It stands for Formula Translating System. Developed by a team at IBM, it was a massive deal. All of a sudden, scientists and engineers could write math formulas pretty much like they would on a piece of paper and have a program called a compiler translated for the computer. This just blew the doors open for a whole new world of software. All right, section 4, an explosion of languages. Once FORTRAN proved this was possible, the floodgates just opened. And this led to a new tool for pretty much every job you can imagine. And this evolution happened fast. In the 50s, you got Lisp for AI research and COBOL for business. The 60s brought BASIC for education. And the 70s? That's when we got C for building powerful operating systems, and SQL for talking to databases. You can see the pattern, right? Each one was a new, specialized tool built for a very specific job. This specialization just kept going, but then one event changed everything: the birth of the public World Wide Web. Suddenly, there was this brand new frontier that needed a completely different kind of software. Interactive, dynamic, and delivered to millions of people. And a whole new generation of languages just exploded onto the scene to meet that challenge. You had Python, designed for simplicity; Java, which promised you could write once, run anywhere, perfect for the internet. And then, in 1995, two giants showed up: PHP for building dynamic websites on the server, and of course, JavaScript, the undisputed king of the web browser. The thing that makes our pages come alive. So on to our last section, Section 5, the programmer's modern toolkit. Where does all this history leave us today? Well, we find echoes of the past in every single line of modern code. If you look at how a modern programmer works, it's a direct reflection of this entire history. It starts with analyzing a problem and designing an algorithm. That's pure Ada Lovelace. Then, you code that algorithm in a high-level language, which gets compiled for the machine. That is Fortran's legacy. Yeah, the tools are way more advanced, but the fundamental logic, it's identical. And the core building blocks, they haven't changed either. Every single programmer today works with algorithms, the plan. They use control structures like if-else statements and for loops, the very ideas that Lovelace introduced. And they all rely on a compiler or an interpreter, that essential translator that bridges the gap between their ideas and the raw hardware. It all connects right back. So, here we are, full circle. The same punched cards that automated the weaving of silk patterns are the direct ancestors of the code that now weaves the entire fabric of our digital society. The core challenge, then and now, has always been about communication. How do we translate human intent into machine action? And as we look to the future, with AI and quantum computing on the horizon, that challenge is still there. The only question is, what amazing new language will we invent to tell those new machines what to do?